All right, so I see some of you have joined back. Let me share this file. Actually, all right. So these are the 3 questions that I asked you to solve. Anybody has any solutions? Let's start with the first one. 13x is congruent to 4 mod 23. Was anybody able to solve this one?
I got x is congruent to 18 mod 23.
Yep, that's correct. Anybody got anything different? Oh, well, that's the only answer. So you're not supposed to get anything different. What is second one? Well, okay, I guess just to go through it. So this first one, 13x is congruent to 4 mod 23. So notice if you double this, right, then you get 26, which is closer to 23 or multiple of 23. So I would multiply the entire equation by 2 first, or congruence by 2, and you get 26x, which is the same as 3x, right, because you subtract 23x. So 3x is congruent to 8, right, and then I could multiply both sides by 8, and I'll get 24x is congruent to 64. Now 24x is 23x plus x, so basically x is congruent to 64, and 64 is 18 mod 23, so that's your answer. What about the second one?
Yeah, I got x congruent to 4 mod 11.
Yep, correct. Again, so the GCD of these two numbers is 2, 12 and 22. So you could divide the entire thing by 2, first of all, because you have to do that first. So you'll get 6x is congruent to 2 mod 11. And then now this isn't divisible by 2. So when you have 6x is congruent to 2, you can just cancel a 2 there without having to worry about this, because this is odd now. So you'll get 3x is congruent to 1 mod 11, right? 3x is congruent to 1. And then you multiply both sides of the congruence by 4, because 4 is relatively prime to 11. And basically you'll get that x has to be congruent to 4 mod 11. Last one.
X congruent to 9 mod 37.
9?
Yeah.
How did you get that one?
We went, suppose we multiply both sides by 2.
Yep.
And you get minus 3x is congruent to 10.
Uh-huh.
Then we multiply both sides by, I believe, 13. So you'll get minus 39x is congruent to 130.
Okay.
So minus 2x is congruent to 130.
Okay.
And then you divide by 2, because 2 and 37 are relatively prime. So you get minus x is congruent to 65.
Okay.
So x is congruent to minus 65.
Uh-huh.
And then, well, you just add 37 2 times to the right-hand side.
Yeah.
Minus 65 plus 74.
Yep.
Which,
yeah, so okay, that gives you 9. Yeah, that's correct. Actually, I made a mistake when I did it. I forget to put in a minus sign. That's why I got something different. But that is correct. All right, good job. I'm sharing the entire screen, so I could just ignore this. Okay, so we are back to this. All right, so these, you all could try those as well. All right, now we're gonna cover 3 very important, okay, 2 very important theorems in number theory, and then 1 not so important one, but sometimes useful. The first one is the not so important one, which is Wilson's theorem. So it says if P is a prime number, then P divides P minus 1 factorial plus 1. Now, you could think of this as P minus 1 factorial would have to be congruent to minus 1 mod P for this to be true, right? Because this would have to be minus 1 so that when you add 1, you'll get 0. This here holds for every prime number. And also the converse is true, meaning that if any number P satisfies this congruence, it must be prime. There's no composite number P satisfying this. Right? Wilson's theorem is kind of complicated to apply unless you have factorial somewhere in the question. So if you see a factorial with a number theory question, you could look out for Wilson's theorem. All right. This one is very important. Fermat's little theorem. But most more complicated number theory questions rely on Fermat's little theorem somewhere. Right, so if P is a prime number and A is a positive integer that is not a multiple of P, right, that's important, A and P are relatively prime, then A to the power of P minus 1 is always congruent to 1 mod P. Right, so if P is prime and you raise A to the power of P minus 1, 1 less than P, you will always get it congruent to 1 mod P. Now, A is relatively prime to P, right? So you can actually multiply both sides of this and get A to the power of P is congruent to A. And this is another way that Fermat's theorem is used more often. Because actually this one holds for all A. A doesn't have to be relatively prime in this one if you think about it. A needed to be relatively prime here because if P divided A, then you would have 1 is congruent to 0, which doesn't make sense. But in this one, if P divides A, then you'll get 0 is congruent to 0, which is true. Right? So with the standard way of using Fermat's little theorem, A and P have to be relatively prime. With this corollary down here, you don't need that condition. So this is for any integer A. Right? So for some examples, if I consider P is 7, right? P minus 1 would be 6. So any number relatively prime to 7, if I raise that to the power 6, I'll always get congruent to 1. 3 to the power 6, 3 3s are 9, 9 is 81. I think that's what, 729 or something like that. Anyway, y'all can work that out. If you check, you'll see that it's congruent to 1 mod 7. If you check mod 5, right, 4 is relatively prime to 5, so 4 to the power 5 minus 1, which is 4 to the power 4, would give you 1 again, mod 5. And if you use the corollary instead, you'll get 4 to the power 5 is congruent to 4, mod 5. Now, what Fermat's little theorem does is it helps you simplify congruences a lot, reduce the powers and stuff. It could also be used in things like this. So for example, if I wanted to prove this is divisible by 15 for all integers, n to the power 33 minus n. All right, that's a big thing to work with. So we need to show that 15 divides that, or in other words, n to the power 33 is congruent to n mod 15. So now 15 is 3 times 5, right? So we could check 3 and 5 separately. So if 3 divides n, all right, if 3 divides this, well, if 3 divides n itself, then obviously 3 would divide this, n to the power 33 minus n, right? Because 3 would divide this and it would divide this. Right? It means that n to the power 33 is congruent to 3 mod, n to the power of 33 is congruent to n mod 3, if n is a multiple of 3. If n is not a multiple of 3, then we could use Fermat's little theorem, right? And we know that n squared is congruent to 1 mod 3. Right? This is not, technically you don't need Fermat's little theorem for this because this follows from what we did before with quadratic residues. We know n squared is always congruent to 0 or 1 mod 3. It would only be 0 if n is a multiple of 3. So if n is relatively prime to 3, then it has to be 1. Right? But anyway, we know that n squared is congruent to 1 mod 3. So I could raise both sides of this to the power 16, right? And I'll get n to the power of 32 is congruent to 1 to the power 16, which is just 1. Now, if I get n to the power 32 is congruent to 1, I can just multiply both sides by n, and I'll get n to the power 33 is congruent to n. Which means that n to the power 33 minus n is congruent to 0, mod 3, right? So n to the power 33 minus n is divisible by 3. So what we've done here in this first part is show that regardless of whether 3 divides n or 3 doesn't divide n, 3 always divides n to the power 33 minus n, right? Or equivalently this. And then we do the same thing for 5. So first check what happens when 5 divides n. Well, when 5 divides n, we know that this is, well, obviously it divides the entire thing. And if 5 doesn't divide n, then we use Fermat's little theorem. And we know that n to the power 4 is congruent to 1 mod 5. So similar to above, we try to get this powers to be 33 basically. That's what we're trying to do. We're trying to get n to the power 33 out of this. And to do that, I could raise both sides to the power of 8. And I'll get n to the power of 4 to the power of 8 will be n to the power of 32. Again, that's congruent to 1. And then multiply both sides by n, and I get something similar to before. So n to the power 33 is congruent to n, implies that basically n to the power 33 minus n is divisible by 5. And that's it. So we've shown divisibility by 3 and divisibility by 5, so automatically it's divisible by 15. This is a question that shows you how you can kind of alternate between divisibility and congruences, because they kind of work hand in hand. They're defined in similar ways.
Yeah, question.
Yeah.
The that raising the power on both sides of a mod, that does not work in the reverse direction.
No, you can't cancel powers.
Right, yeah.
You can't take roots, right? I forgot to mention that. It's a good thing you asked. You can't take roots when you're dealing with congruences. That's one thing you have to be careful of.
Cool.
And when you're dividing, you have to make sure you're dividing by something that's relatively prime to the mod. If you're not dividing by something that's relatively prime to the mod, you have to divide throughout, including the mod, whatever this number was. That's the two things you have to be careful with. Before we go on to Euler's theorem, which is a generalization of Fermat's, I want to show you something. Right, there's one of the questions in a miscellaneous exercise use something called fractional modular arithmetic, which isn't actually explained in the notes, but I just wanted to show you how it works. Right, so basically how it works is that if you have a fraction, right, consider this fraction, 851 divided by 37. You can do two operations on this. You can either multiply the top and bottom by any number that's relatively prime to the modulus, or you could, from either the top or the bottom, you could add or subtract a multiple of the modulo. Right? This is just an example to show you how it works. So I could actually divide this myself and say, well, this thing is equal to 23, right? But if the question was to find the last digit of this number without actually dividing it just manually, you could do that using fractional arithmetic, fractional modular arithmetic. Now, if you want the last digit, right, it means you want to know what this number is mod 10. So we want to know what 851 divided by 37 is mod 10. So to do that, I could start with, well, 851 is congruent to 1 mod 10. 37 is congruent to 7. So this fraction is actually congruent to 1 over 7. Right? And then what I could do is, well, I'm trying to get, basically what you're trying to do is make the denominator 1 somehow by using multiplication and then addition and subtraction. So I'll need to multiply this by something. If I multiply it by 3, then this will become 21, which is 20 plus 1. So that's nice. But when you're multiplying, you have to do it in both numerator and denominator. When you're subtracting or adding, it could be in either or. So I could multiply it by 3 and I'll get 3 over 21. Right? And then I could just subtract 20 from the denominator and I'll get 3 over 1. And 3 over 1 is just 3. Right? So it means that I could use fractional modular arithmetic to figure out what the last digit of this number is by considering mod 10. And it would be 3, rather than actually dividing it. So if it was something that's really complicated, then you don't actually want to go and long divide that. Right? So then you might use something like this. This isn't something you have to know, but it is useful when you have things dealing with fractions. Any questions about this what we just discussed here? Okay, let me just make sure you all understand how this works. So what I want you to do is, let me find something that's actually an integer. so what I want you to do is find out, tell me what the answer is if I take the number 11,931 and divided by 123. All right, that works out to be an integer, but I don't want you to long divide it. I want you to tell me what this number works out to be, or what the remainder of this number is when I divide it by 7. All right, so basically what I want to know what 11,931 divided by 123 is considered mod 7. So it's not the last digit we're looking for anymore, it's mod 7. So it's all different. Let me know when somebody has an answer. All right, so this is a question basically. This number divided by that, what is the answer mod 7 without actually dividing the number itself? So I want you to use fractional arithmetic.
But Jags,
Yeah.
when you're using like, instead of using this whole fractional arithmetic, right? And we could just like replace those question marks with an X and then multiply by 123 and then just do it like a regular congruence.
Yeah, you could do it that way as well.
Okay.
But when well, it works. It's just like it just takes a lot more time to actually write it out and figure out what to do with it. If you're comfortable, once you get comfortable using fractional arithmetic, this is actually faster. Because you don't have to keep writing the X everywhere, it's just a fraction you're writing.
Right.
Anybody has an answer?
Yeah.
There are only 7 possible answers, right? 0 to 6. So which one is it?
I have answers, but say it out loud now. Or,
Yeah.
I get X congruent is 6 mod 7.
Yeah, that's correct. If you divide 123 by 7, right, you'll get remainder 53, that's 4. The remainder here is 4. 119 is divisible by 7, so the remainder would be 28 plus 3, the remainder is 3. So basically this fraction is congruent to 3 over 4 mod 7, and it just multiply above and below by 2, and basically you get the answer. You get 6 over 8, which is the same as 6 over 7, 6 over 1. So yeah, that's it. All right, finished with this. I'll close that. All right, 2 more things we're gonna cover here. So Euler's theorem and Chinese remainder theorem. Before we cover Euler's theorem, we need to know what this thing is, the Euler-Toshan function. right? And it's defined as using the symbol phi of m. Now what this does, it basically counts the number of positive integers less than or equal to m that are relatively prime to m. And one thing you have to bear in mind when you're doing this is 1 is always counted. So you always count 1 because 1 is relatively prime to everything. So for 1, phi of 1 will be 1 because 1 is relatively prime with itself. Phi of 2 is 1 because again 1 is the only number that works. So basically you start from 1 and you keep going till you get to m and then you check all the ones that are relatively prime. For m is equal to 3, both 1 and 2 are relatively prime to 3, so the answer is 2. Yeah, 2 of those. For 4, that would be 1 and 3, so 2 of those. Now 5 is prime, right? So 5 is relatively prime with 1, 2, 3, and 4. That's 4 numbers. For 6, it would be 1 and 5. Those are the relatively prime ones. And you could keep going like that. There isn't a close, like a close formula for how you do it. You just have to kind of do it based on the ones that come before. There are properties you can use to figure out what it is. So for example, if p is prime, phi of p is always going to be p minus 1 because it's going to be relatively prime with everything less than itself. Right? So from 1 to p minus 1 will all be relatively prime, and that represents p minus 1 numbers. Right? If p is prime and p is a positive integer, then if you consider a power of p, so if you want phi of p to the power k, the answer actually works out to be p to the power k minus p to the power k minus 1. Right? And well, there's a proof here. The reason why it works is because you could actually count the number of numbers from 1 to p to the power k that have p as a factor, and that is basically just a floor using the formula we had done above. The floor of p to the power k divided by p. That's the number of multiples of p from 1 to p to the power of k, right? And that works out to be this. So if you know that this many numbers are divisible by p, you just subtract that from the total number, which is p to the power of k, and you get your answer. Right? So for example, phi of 5 is 4, right? So if I wanted to figure out what phi of 125 is, right? Phi of 125 is phi of 5 cubed. Right? The answer would be 5 cubed minus 5 squared. So basically the answer would be 100. 125 minus 25. Right? So these are two properties used. There's a third one, which is the most important one, I think. So if A and B are relatively prime, then phi of the product of A and B is just phi of A times phi of B. This is called a multiplicative property, but it only works if A and B are relatively prime. For example, if A was 2 and B was 4, then you can't use this. If A is 2 and B is 5, then yes, you could use it. Right? So phi of 10 is phi of 2 times phi of 5. Phi of 2 is 1, phi of 5 is 4. So the answer just works out to be 4. Right? So once you know how the Euler torsion function works, then we could define or could state what Euler's theorem is. Euler's theorem says that if m is a positive integer and a is an integer relatively prime with m, meaning that the GCD is 1, then a to the power of phi of m is the Euler torsion function of m. So a to the power of that is congruent to 1 mod m. Right? Now note that if m is prime, then phi of m is going to be p minus 1, and this thing is going to reduce the Fermat's-Little theorem. Right? So Fermat's-Little theorem is a special case of this when m is prime. But this thing is more general. M doesn't have to be prime for this to this to hold. Right? So let's see. So if a is 5 and m is 6, right? Phi of 6 is 2. You could calculate that, or you could maybe found it above. So it means that 5 to the power of 2 is 1 mod 6. Phi of 8, now 8 is 2 cubed, right? So phi of 8 should be 2 cubed minus 2 squared, which is 4, basically all the odd numbers. So 3 to the power of 4 is going to be 1 mod 8. Or 5 to the power of 4, or 7 to the power of 4, or 1 to the power of 4. Any odd number to the power of 4 will be 1 mod 8. And for 10, now this is useful, right? If you want to know the last digit of a number, you could use Euler's theorem. Because if you have like some weird problem, because phi of 10 is 4, so it means that any number to the power of 4, any number that's relatively prime to 10, if you raise that number to the power of 4, you'll get 1 mod 10. So you could actually use that, right? If I wanted to know what's the last digit of 237 to the power of 8, so 237 to the power of 8, you could just say, well, 237 to the power of 4 is 1, so you just square both sides. And the answer is again 1. Now, for things like this, for the last digit, then, I mean, you know, intuitively, you could just say, well, okay, the last digit is 7. If I multiply 7 by itself 4 times, the answer will be 1, right? But it's not so simple when you have to do things like the last 2 digits and the last 3 digits. This one, Euler's theorem, is much more useful. So, first of all, if you want to use an Euler's theorem to get the last 2 digits, you're going to need to know what phi of 100 is, because you need to consider mod 100. So phi of 100 is phi of 4 by phi of 25, right? These you could work out. Phi of 4 is just, you can calculate that manually. Phi of 25, you could do it manually, you could use the formula. This is the same as 25 minus 5, right? 5 squared minus 5 to the power 1. So you get 20. Anyway, phi of 100 is 40. It means that 13 to the power 40 would always be congruent to 1 by Euler's theorem. Right, mod 100. So the reason why I have 13 to the power 40 is because the number we have here is 13, right? If this was 17, then I would say, okay, 17 to the power 40 is 1. But anyway, so 13 to the power 40 is 1. So if I square both sides of this, 13 to the power 80 is also 1. But I want 13 to the power 82. So I just need to multiply both sides by 13 squared, and I'll be done. Right? Because 80 plus 2 will give you 82. So this is what we get. Right? So we had this, multiply both sides by 13 squared, and we get this, and 13 squared is 169. So basically what that means is the answer is 69. That's the last 2 digits. Right? And that's how you use Euler's theorem for something like this. Now, it's straightforward like this when you have numbers to consider, but sometimes you use it with variables as well. So those are things you'll have to learn with practice. All right, before we do, Chinese remainder theorem, I want you to do these 2 questions. You'll need this one to do this one. All right, might have to pause and then come back to Chinese remainder theorem after. So first of all, tell me what phi of 1000 is. How do you work that out? What's the prime factorization of 1000?
5 cubed, 2 cubed.
2 cubed by 5 cubed, right?
Yeah.
So what's phi of 2 cubed? Phi of 8. You could check it manually. You could say, well, 2 cubed, for 2 cubed, phi of 2 cubed will be 2 cubed minus 2 squared using the theorem. So the answer will be 4. What about phi of 5 cubed? This one I had actually worked out for you already.
Should be the 5 cubed minus 5 squared.
Yeah. So 125 minus 29 would be 100. So basically phi of 1000 is going to be 400. So any number raised to the power of 400, any number is relatively prime to 1000, raised to the power of 400 is going to be congruent to 1 mod 1000, meaning when you divide the number by 1000, the remainder is always going to be 1. So using that argument, 17 to the power of 400 must be congruent to 1 mod 1,000. 17 and 1,000 are relatively prime. Right? Using Euler's theorem. Now, if 17 to the power of 400 is congruent to 1, I'm trying to get as close to 2,000 as possible. So let me multiply by 5, right? Because 400 by 5 is 2,000. So I said multiply, but actually raise everything to the power of 5. So what you're going to do is raise 17 to the power of 400. You're raising that to the power of 5. And then laws of powers, exponents, you multiply the 5 and the 400. So you get 17 to the power of 2,000 is 1. It means that 17 to the power of 2001 will be 17. You multiply both sides by 17. So for this one, the answer is actually 017. Those are the last 3 digits. Right? Because 17 to the power of 2001 is congruent to 17 mod 1,000. There's some nice questions in here for you all to prove, so I hope you try them. 5, 6, and 7 in particular. If you these are nice to prove, but they're also nice to know. So if you could remember these for later on, sometimes these, especially this one, can be helpful in more complicated problems. This one in particular, this goes very well with Fermat's theorem in a lot of the more complicated problems you will see. These ones are more specific. All right, this one down here is Wilson's theorem, if you want to try it. Wilson's theorem and fractional arithmetic if you want to use it, but you don't need it. All right, we have 5 minutes for this thing cuts off again. I wouldn't be able to finish Chinese remainder theorem in that time, so we'll have to let it cut off and then restart. So I will give you a, I guess take a 5-minute break and then we'll start back, or 6-minute break and we'll start back at 4:50. That last session will be long. It's only Chinese remainder theorem we have to do. Any questions in the remaining 5 minutes we have here? Based on what we just discussed, anything to do with congruences? I really want you all to try these questions here, because these questions will give you a good feel of how you use congruences and how you use Fermat's and Euler's. All right, so you can try it and then you have the solutions so you can look at them.